All right, welcome to 5.2, the definite integral. What's this integral thing? Integral is the new name for antiderivative. So no more antiderivative. We're going to start focusing on the word integral. All right, so last section we used rectangles, Riemann sums, to estimate the area under a curve. We can get a better approximation if we use more rectangles, kind of like we talked about at the very end of the video in part 2. Let's come up with a formula that will help calculate the area under a curve using a large number of rectangles more quickly. So we're going to go to sigma notation. The sum of n terms, a sub 1, a sub 2, a sub 3, all the way up to a sub n is written as the summation as I equals 1 to n of a sub I. This would be some kind of sequence function, equals a sub 1 plus a sub 2 plus a sub 3 plus all the way up to a sub n, where we call I is the index. Now your I can be any variable. It could be a k, it could be x, it could be n, whatever variable you so choose. They have chosen to use I here. Not one of my favorite because too many people get that confused with the imaginary number. So this is just a counter index for us in our summation. So a sub I is the ith term of the sum. And the upper and lower bounds of summations are n and 1. So the upper bound is n, that's the last term. The lower bound will be the 1. That's the very first number we start with. So lower bound on the bottom, upper bound on the top. All right, so if we were to ask to find the summation of I equals 1 to 36, by this definition, we have to put a 1 in for I. 3 times 1 is 3, plus 4, that would be 7. Then we got to put in a 2. 3 times 2 is 6, plus 4, that would be a 10. And we would have to do then the 3 goes in for I, and we'd have to do this all the way up to 36. I don't know about you, but this could be tough having to find 36 numbers and then go ahead and add them all together. So what we could do is we could break this up into some nice little identities that we have for our summations. This one here, the first one, says that, look, if you have some kind of scalar value or a coefficient being multiplied to your changing variable, your I, then just factor it out in front so you don't have to multiply by 36 times. And the second one here says, look, if you're adding two things or subtracting two things inside your summation, you could separate them. So instead of adding 4 all the time, we could just take out all the 4s and just add the 4s together. All right, so by separating these into two summations, 3 times the summation of I to 36 of just the I, or I equals 1, excuse me, and then I equals 1 to 36 of the 4, we could crunch the numbers here a little bit quicker, because then we can go 3 times 1 plus 2 plus 3 plus 4 all the way up to 36. And then the last one, well, wait a minute, if you add 36 4s together, that's the definition of multiplying. We can say 36 times 4. Okay, so crunching the numbers, add that all up, I get 666 times 3, 36 times 4 is 144. We get 2,142. All right, we can do this even faster. We don't have to add any of these numbers together. We can do them faster. We have more summation properties. And if you had a really good college algebra teacher, they talked about these. So the the summation of 1 to n of just some constant number is the constant times n. Here's the 3 that are important. If it's going to be a linear sequence, your variable is to the first term. There's the formula to add up n number of terms, n times n plus 1 all divided by 2. If I have I squared, that's n times n plus 1 times 2n plus 1 all divided by 6. And if I have I to the third as one of my variables, it's n times n plus 1 all over 2. The exact same as up above here, but then you square the whole thing. And if you want to square it all out, you can say n squared plus n plus 1, that binomial squared over 4. I prefer to use this. And if you notice really close, all three of these are closely related. All right? Notice in the I squared, here's n times n plus 1. Same as the top here and here. But they have one extra binomial. Now, a way you can remember that is look at what you've already written down. I have two n's, 2n, plus a 1, plus a 1. We just have to remember that the denominator is now 6, not 2. Another cool pattern that you'll notice is that here there's no n or I or any variable on your constant. That means 0 of them. Then you have to use 1n. Here it's I to the first power. I have to use 2 n's being multiplied together in some way, shape, or form. Here's I squared. How many n terms being multiplied? 3. I to the third. Well, following the pattern, 0, then 1n, 1 for a power, then 2 n's. I squared, 3 n's. I cubed should be 4 n's. All right, 1, 2, that's 2 squared makes it 4. So there's a definite pattern there. All right, so if I go back to that previous example, I equals 1 to 36 for the summation of 3i plus 4, and do the same thing what we did is broke it down to two summations. There's the 36 times 4, like we did previously. Now, instead of adding up 1 through 36, let's just use the formula here. N is 36 times 36 plus 1, all divided by 2. Now, one thing should be understood. We are working with integers here. 1 through 36 are integers. So you plug that into a polynomial, you will get integers, which means there should be no fractional answers when you add integers. So that means this denominator of 2 has to cancel with somebody. Well, 2 can go into 36 18 times. So now my answer is, go to the calculator, 3 times 18 times 37 plus 36 times 4, 2,142. So we're going to want to have these formulas handy for us. It's going to make, when our n is going to be incredibly huge, when they said, oh, we're going to find the area under this curve and we're going to use 36 rectangles. All right, now, if you get lost here, make sure you re-look at the video. You want to hear this again. With our summations here, these properties, these formulas, along with our right endpoint, left endpoint, midpoint, and you can see why a lot of our formulas at the end of the last section's video wanted to use R sub n, because this is a nice, short, sweet formula that we're going to use. So let me demonstrate these three right here. Using summation notation, approximate the area under the curve of f of x equals x squared plus 3 on the interval of 0 to 4 using 8 rectangles and using right endpoints. So this is the formula we're going to use. Now, that delta x, that change in x, that doesn't change. All right, that's 4b minus a, 0, divided by the number of rectangles. We want 8, so 4 over 8 is 1/2. That's your change in x. This is always going to be 1/2 right here. Now, what's key is, what's this x sub I going to be? Well, x sub I will equal a, which in this case is 0, plus I times the change in x. So we had a 0 for a, let's put that in, plus I times 1/2, that's your change in x. So that's going to give us I over 2. That's my x sub I. So that we're going to replace right here. And in doing so, this is my function now in my summation from I equals 1 to 8. And now f of I, so when I is 1, we'll put a 1 here. When I is 2, we'll put a 2. Then a 3, a 4, a 5, a 6, a 7, and 8. All right, so one thing that you can do is you can take out this 1/2. That's like that scalar factor, that coefficient. And let's factor it out in front of the summation. And now we're going to take this I over 2, and we're going to substitute it into our f function right here. So that's going to give me I over 2 squared plus 3. Well, we don't want to crunch out all these numbers. What we're going to do is we're going to simplify the inside. All right, so this becomes I squared over 4. Again, there's a scalar factor right here, whether it's being multiplied or divided. So that division of 4 is like saying we're going to multiply by 1/4 to all of our terms. No, we're not. Let's just factor it out to the front like we did the 1/2. The least amount of work on the inside, the better. So we're going to factor that out. I haven't done it yet. I'll get to it. And then we're going to separate into two summations. So I separated them first. So this 1/2 goes with the summation for both of those. Okay, here's where I factored out the 1/4 out to the front. So this first one is 1/8 times the summation of I equals 1 to 8 of I squared plus 1/2 times the summation of I equals 1 to 8 of 3. So let's now go to our formulas. We have an I squared, we need this formula. And I have a constant, we need this formula. So I squared, n is 8, times n plus 1, 8 plus 1, times 2 times n, 2 times 8 plus 1, all over 6, plus the 1/2 times 3 times 8, and don't forget to bring that 1/8 and multiply it to this part. So what we want to do is crunch the numbers inside the parentheses. Now again, remember, these denominators will disappear. 6, well, let's see. We got 2 can go into 8 and 6, and 3 can go into 9 and 6. So we're going to steal a 3 from the 9, a 2 from the 8, and cancel that with the 6. 17 is not going to do us any good there. So this gives me 1/8 times 4 times 3 times 17, plus here was 24 times a half, 12, and this is all 37.5. Okay, and that's how we use this rule. We're going to have to make sure you know that for the test. If you're going to do a right endpoint, we can take this adjustment to your x sub I into your function, and then we can use our summations for it. All right, so now let's do part B. Let's do left endpoints. Same as before. 0 to 4, 8 rectangles, same change in x. But now we have to use this formula right here. So my x sub I equals a, which was 0, plus I minus 1 times a half. And this will give me the values that I want to use in my function for left endpoints. So that means my summation of 1 to 8 of f of 1/2 times I minus 1 times a half. Again, remember the 1/2 here, that's the change in x that we're multiplying by. So again, think of your rectangles. This is the base, this is the height. The f of x sub I is the height. Well, again, we're going to factor out the 1/2 to the front and focus on what we have here. Then we're going to have to substitute 1/2 times I minus 1 into our function for x. So that's why we see all of this in a big set of parentheses being squared, because it's going in for all of x. So you got to remember, bring the 1/2 in there too. So we got to FOIL this out. So 1/2 squared is 1/4, and then we're going to FOIL out the I minus 1 squared. Oh, wait, before we do that, let's separate them into two summations. So 1/2 times the summation of 1/4 times I minus 1 squared plus 1/2 times the summation of just the constant 3. Now we'll FOIL this out. But again, we don't want the 1/4 here. I factored it out to the front, made that 1/8. I FOILed this out. I minus 1 squared is I squared minus 2I plus 1. And over here, 1/2 times 8 times 3 is 24, so that's the same plus 12 as we had in the previous example. All right, so now we need to use our summations. We're going to break it down to 3 separate summations. One for the I squared, one for the minus 2I, one for the plus 1. So 1/8 times, here's the I squared formula, 8 times 8 plus 1 times 2 times 8 plus I, 1, minus 2, I is linear, so we use this formula, 8 times 8 plus 1, and then you have the 1 at the end, so you use your constant, 8 times 1. Again, everything on the inside here, fractions, should cancel. So 8, 9, 17 will do the same thing. A 2 from the 8, a 3 from the 9 cancels a 6, leaving us 4 and 3. Here, the 2 can cancel with this 2 that's going to be multiplied to it, or you could cancel with that 8. Either one's fine. And now we have 1/8 times 4 times 3 times 17 minus 8 times 9 plus 8 plus the 12 that we had right here. And go to the calculator, crunch the numbers, we get 29.5. All right. Midpoint. Everything stays the same for a change in x. But now we're going to use this formula, which, oh boy, has a fraction in it. Oh, it's going to make this harder. Okay, let's go to work. X sub I equals A, which is 0, plus I minus 1/2 times 1/2. All right, so F of 1/2 times I minus 1/2. So it's pretty much the same as what we had previously, but it was I minus 1. Now it's I minus 1/2. That's what makes the midpoint more difficult to work with, is because we have that fraction, we have more fractions. So again, factoring this 1/2 out to the front. Again, we're going to have to clean this up. So we're going to square the 1/2 like we did before to make it 1/4. Then I minus 1/2 squared. Here we're going to now break this into two summations like we did earlier. So 1/2 times the summation of this term, 1/4 times the binomial being squared, plus 1/2 times the summation of just the constant. Well, again, this is exactly the same as the last two examples. That's a 12, so I'm not going to write this anymore. But here, we're going to want to factor out the 1/4 to make it 1/8. Like I said, there's the plus 12 at the end. FOIL this out, I squared minus I plus 1/4. Again, break this summation into your three formulas, the I squared, the I, and your constant. So that's the next thing. So 1/8 again. Here's the same thing we saw before, where that turns into a 9. That's a 17, and we canceled here to cancel the 6. Here the 2 can go into the 8 4 times, cancels that out. Here the 4 can go into the 8 twice. So like I said, inside that summation, there should be no fractions left over. So this is 1/8 times the 4 times the 3 times the 17 minus 4 times 9 plus 2. And then don't forget the plus 12. And so all of this became the 21.25 plus 12 is 33.25, which gives me a much better approximation. All right, so we're going to end it right there. And we'll come back with part 2 in just a minute.